Imagine, just for a second, a massive, blazing bonfire. It's roaring, crackling, putting out an immense amount of heat. I mean, so much that you can't even get close to it.
An inferno.
An inferno, exactly. Now, imagine you are standing miles away, shivering in the dark, and you manage to catch a single spark, just a microscopic, fleeting speck of heat from that entire fire.
Okay.
That is essentially what our planet is working with. And here's a mind-bending fact to kick things off today. The Earth receives only 1 in 2 billion parts of the sun's energy.
1 in 2 billion. It sounds like a statistical error, doesn't it? It sounds like nothing.
It does. It sounds completely negligible. And yet that tiny, infinitesimal fraction is the engine for everything. It drives every storm, every breeze, every single weather event we have ever experienced.
It really puts the fragility and the efficiency of our system into perspective. We often view the sun as this overwhelming force, which of course physically it is, but the delicate balance of life here depends on us catching just that specific tiny sip of energy.
Yes, sip, yeah.
If we got a little more, we'd burn. If we got a little less, we'd freeze. This conversation we're having right now just wouldn't be happening.
Exactly. It's a wild thought to start your day with. Welcome back, everyone, to a very special edition of The Deep Dive. We are deviating a little from our usual path today because this deep dive is custom-tailored for a very specific, very dedicated group of listeners, our UPSC aspirants.
That's right. And this one is brought to you by the Simplified UPSC by PPP YouTube channel.
It is.
And the mission today is specific. We aren't just reading a textbook, we are decoding. We are taking a deep dive into NCERT Class 7 Geography, Chapter 4, simply titled Air.
Air.
Now, I know what some of you might be thinking, Class 7, I'm preparing for the civil services, one of the toughest exams in the world, not a middle school quiz.
I think that's a common trap, right?
Yeah.
Overlooking the basics because they seem too simple.
It is the biggest trap because we aren't just staying in the 7th grade. We are going to link these foundational concepts directly to previous year questions, or PYQs. We're going to show you how a sentence in a 7th grade book evolves into the complex, tricky questions you face in the actual civil services exam. If you don't have the foundation, the skyscraper, well, it collapses.
We have a lot of ground, or I guess I should say sky, to cover today. But before we launch into the atmosphere, I have a humble request for all you dedicated learners out there. We put a lot of work into synthesizing these sources to make your prep easier. If you find value in what we're doing, if these deep dives help you connect the dots, please subscribe to the Simplified UPSC by PPP channel. It really supports our mission to keep bringing you this super useful content.
And for those who are capable and want to ensure the continuity of this series, because high-quality research does take resources, please consider supporting us on Patreon. It makes a huge difference in our ability to keep the lights on and the content flowing.
A huge shout out to our current supporters. You guys are literally the wind beneath our wings. Pun absolutely intended there. Also, don't forget to hit that like button on the video or audio, and please share your thoughts in the comments. We actually read them, and it helps us tune the show to exactly what you need.
One last bit of housekeeping before we start. We know you need materials to study, not just audio. So we've made free notes with practice PYQs available on our public Telegram channel.
And for the serious, intense preparation, if you want to save time and get straight to the meat, we have the private Telegram library. This gives you access to all videos in this series at once, organized premium notes, detailed explanations, extra PYQs, and even model mains answers.
It's the full package.
It is. If you want in on that, just DM us on the public Telegram channel.
All right. Housekeeping done. Let's set the stage. We were talking about air.
Right. To the average person, air is just, well, it's nothing. It's the empty space between me and you. If I wave my hand in front of my face, I'm waving it through nothing. But geographically speaking, scientifically speaking, it's not empty at all, is it?
Far from it. It is a dynamic physical substance. It has weight, it has mass, it has structure. The NCERT describes the atmosphere as a huge blanket surrounding the Earth.
A blanket.
And that word blanket is chosen very carefully. It's integral to the biosphere. It provides the air we breathe, obviously, but its role as a shield is even more critical. It protects us from the harmful effects of the sun's rays.
So without this blanket, we'd be baked alive by day and frozen solid by night.
Instantly. It's Earth's climate control system.
Right.
Precisely. It moderates the temperature to make Earth livable. Today, we're going to break this down into a roadmap. We'll look at the composition of the atmosphere, what is actually in that soup we breathe.
The soup we breathe, I like that.
We will look at the structure, the layer cake of the sky. Then we'll tackle the difference between weather and climate. And finally, the mechanics of the invisible engines, wind and rainfall.
Okay, let's jump into segment one, the soup we breathe. So this idea that air isn't just one thing, it's a mixture.
It's a cocktail of gases. If you look at figure 4.1 in the text, it breaks it down clearly, and the proportions are often surprising to people who haven't looked at this since school. The vast majority, a whopping 78%, is nitrogen.
Which I think trips people up. We tend to think, I breathe oxygen, I need oxygen to live, so air must be mostly oxygen. But nitrogen is the heavyweight champ here. Why so much?
Well, nitrogen acts as a stabilizer. If the atmosphere were, say, 100% oxygen, the world would be incredibly volatile. Fires would just explode out of control. Biological processes would run way too fast. So nitrogen dilutes the oxygen. But here is the interesting biological paradox. While we don't breathe nitrogen directly, in fact, we inhale it and exhale it right back out without using it, plants absolutely need it to survive. It's a building block of life.
But here's the catch mentioned in the text. Plants can't take nitrogen directly from the air either, so it's floating all around them, but they can't eat it.
Exactly. It's like being thirsty in the middle of the ocean water everywhere, but you can't drink it. Plants need a middleman. There are specific bacteria, rhizobium is the classic example, that live in the soil and in the roots of some plants, especially legumes.
Okay.
These bacteria take the atmospheric nitrogen and change its form, they fix it, into a form that plants can absorb through their roots.
They're like nature's little translators. Okay, so nitrogen is the bulk, but it's chemically inert for us humans. Then we have oxygen coming in second at 21%.
The breath of life. Humans and animals inhale it, and green plants produce it during photosynthesis. This creates a perfect symbiotic cycle. We breathe in oxygen, breathe out carbon dioxide. Plants take that carbon dioxide, use sunlight, and make oxygen. It's beautiful.
But the text mentions a warning here. This balance stays perfect, unless we mess with it.
Right. The system assumes a steady state. If we cut down trees, we are removing the oxygen factories. That disturbs the balance. We are consuming oxygen and producing CO2, but we are destroying the very mechanism that recycles it back.
Then we have the trace gases. Argon is about 0.93%, and then there's carbon dioxide at 0.03%, plus tiny amounts of helium, ozone, hydrogen, dust particles.
I want to zoom in on carbon dioxide, or CO2.
Yeah, let's.
It gets such a bad rap these days for obvious reasons, but the text calls it an important gas.
It is vital. And for UPSC aspirants, understanding the dual nature of CO2 is critical. You have to separate the natural function from the anthropogenic or human-caused excess. There is the good CO2, which creates the greenhouse effect.
Explain that for us. Why is the greenhouse effect good? We usually hear it as a doomsday term. The greenhouse effect is killing us.
That's a colloquial misuse of the term. The greenhouse effect is a natural and essential phenomenon. Think about a greenhouse in a garden. The glass lets the sunlight in.
But when that light hits the plants and soil, it turns into heat. The glass stops that heat from escaping. The atmosphere does the same thing. Gases like CO2 allow the sun's shortwave radiation to enter, but when the Earth radiates that heat back out as longwave radiation, CO2 traps it.
And without that
natural greenhouse effect, Earth would be a frozen rock. We'd be Mars. The average temperature would be way, way below freezing. So CO2 traps heat and keeps the planet warm enough for life to exist. That is the good part.
Okay, so we need a blanket, but the problem is we're piling on too many blankets.
Exactly. That is the bad side, global warming. When we burn fossil fuels like coal and oil, we release billions of tons of extra CO2 into the atmosphere. This volume is unnatural. It's like adding a dozen extra blankets.
So it traps too much heat.
Way too much. The text explicitly links this to rising sea levels, melting snow in cold regions, and flooding coastal areas. It's a direct chain of consequences.
This is where we need to bring in the UPSC lens. This isn't just 7th grade science. This is the basis for high-level questions. How does this basic gas composition play out in the exams?
Absolutely. Let's look at the connection to the 2019 prelims, paper 1. There was a question regarding wetlands and their role. It touched on carbon releases and methane.
Okay.
Wetlands are actually huge carbon sinks. They store carbon, but if they're disturbed or as temperatures rise, they can release greenhouse gases. You have to understand the basic carbon cycle described here in NCERT to even begin to answer that question.
And looking at the 2025 prelims paper 1 source we have, specifically question 29 regarding the atmosphere, it had a statement. Atmosphere's gases like carbon dioxide are particularly good at absorbing and trapping radiation.
That is a direct application of this chapter. The statement is correct. If you understand the NCERT concept that CO2 creates a greenhouse effect by trapping heat, you get that mark. It seems simple, but in the pressure of the exam, people second-guess themselves.
They overthink it.
They think, is it particularly good? Or just sort of good? The answer is yes. It is the primary mechanism for terrestrial radiation trapping. It's foundational knowledge.
It also links to the 2016 prelims, question 86, which asked about the air quality index. It listed gases like carbon monoxide, nitrogen dioxide, and sulfur dioxide.
Right. While the NCERT Chapter 4 focuses on the main atmospheric gases, the UPSC extends this to pollutants that alter that composition. You need to know the normal composition from NCERT to identify the abnormal pollutants from current affairs.
So CO2 isn't usually in the AQI.
No, because it's a natural part of air. But carbon monoxide from incomplete combustion is a deadly poison. You need to know the difference.
So the takeaway is know your gases, know what they do naturally, and know what happens when humans add too much of them.
Correct. It's about baseline versus anomaly.
Okay, let's move up, literally. Segment 2. The layer cake, or the structure of the atmosphere. The text says our atmosphere extends up to about 1,600 kilometers, but it's divided into 5 distinct layers.
Think of it like a 5-story building, but the floors get weirdly different as you go up. The rules of physics, or at least how we experience them, change on every floor.
Ground floor, the troposphere.
This is the life layer. It goes up to an average height of about 13 kilometers. This is where we are right now. The air we breathe is here. And crucially for geography, almost all weather phenomena happen here.
All of it.
Almost all of it. Rainfall, fog, hailstorms, it's all happening in the troposphere.
So if it's raining, you can blame the troposphere. But why only here? Why don't we get rain higher up?
Great question, because this is where the water vapor is. Also, this is where the dust particles are, which act as nuclei for clouds to form. And most importantly, the temperature decreases as you go up in this layer. This creates the instability needed for air to move up and down, which is what drives weather.
And here is a key PYQ connection. In the 2024 prelims, question 12 asked about water vapor. One of the statements was that the amount of water vapor decreases with altitude.
That is true, and it aligns perfectly with the structure of the troposphere. Most of the moisture is hugging the surface because gravity pulls the heavier particles down. It's a dense, wet layer at the bottom.
Also, the 2013 prelims question 16 asked about freshwater distribution. It noted that a portion exists in the atmosphere as moisture and clouds. That is practically all residing in this bottom layer.
Exactly. All roads lead back to the troposphere for weather. Okay, moving up to the second floor, the stratosphere. This extends up to 50 kilometers.
This is the VIP lounge for airplanes, right?
It is. Pilots love the stratosphere. Why? Because it's above the weather. No clouds, no storms, much less turbulence. If you've ever been on a plane and it's bumpy during takeoff and then suddenly it gets super smooth, you've just crossed the tropopause and entered the stratosphere.
But biologically, its most important feature isn't smooth flights. It's the ozone layer.
Yes. We talked about oxygen O2, but ozone is a specific form of oxygen O3 that absorbs harmful ultraviolet rays from the sun. Without the stratosphere's ozone, we'd have serious radiation issues down here. Skin cancer rates would skyrocket, crops would fail.
Now, here is a weird thing about the stratosphere. In the troposphere, as you go up, it gets colder. We all know that. But in the stratosphere, as you go up, it gets warmer. Why is that?
That's because of the ozone. The ozone layer is absorbing that UV radiation from the sun. When it absorbs that energy, it converts it to heat. So the stratosphere is actually generating its own heat source in a way. It's a temperature inversion.
Okay, third floor, the mesosphere, up to 80 kilometers.
Meso means middle. This is the shield in an action movie sense. This is where meteorites burn up. When you see a shooting star, you are likely looking at a rock hitting the mesosphere and incinerating.
Why do they burn up there?
Friction. Even though the air is incredibly thin compared to the ground, it's thick enough that when a rock hits it at 30,000 miles per hour, the friction creates intense heat. It turns the rock into ash before it can hit our heads.
It's the atmosphere's incinerator.
It is. And note the temperature flip again. In the mesosphere, temperature starts dropping again. In fact, the top of the mesosphere is the coldest place in the atmosphere.
So we go cold, troposphere, hot, stratosphere, cold again, mesosphere. Next up, the thermosphere. 80 to 400 kilometers.
The name gives it away. Thermo means heat. Temperature rises very, very rapidly here. We're getting closer to the raw solar radiation. But the key feature for us is the ionosphere, which is a part of this layer. This is the tech layer.
The tech layer.
Yes, because it makes long-distance radio transmission possible.
How does that work?
Radio waves are basically light waves. They travel in straight lines. But the Earth is curved, so if I send a radio signal from New York to London, the curve of the Earth blocks it. But the ionosphere contains electrically charged particles, ions. Radio waves sent from Earth bounce off these ions and are reflected back to Earth, effectively curving around the planet.
So without the thermosphere, no long-distance AM radio.
Correct. And finally, the penthouse, the exosphere, the uppermost layer. The air is incredibly thin here. Light gases like helium and hydrogen are just barely hanging on, floating off into space.
It's the frontier, the transition zone into the void. So to recap, troposphere for weather, stratosphere for flights and ozone, mesosphere for burning meteors, thermosphere for radio and heat, and exosphere for the exit.
And remember that temperatures zigzag. Falls, rises, falls, rises. That pattern is often a trap in exams where they ask you to plot temperature against altitude.
Speaking of temperature, let's slide into segment 3, weather, climate, and temperature. I think people use weather and climate interchangeably in casual conversation, but in geography, they're very different things.
They are. The NCERT uses a great analogy. If the body is a radio, weather is the fiddling with the knobs. It's hour to hour, day to day. It can be sunny in the morning and raining by lunch. It's dramatic and short term.
Whereas climate is the setting you generally leave the radio on.
Precisely. Climate is the average weather condition over a long period, usually 30 years or more. So you can have a rainy day in a desert climate. The weather is rain. The climate is still arid. This is important for understanding things like climate change. We aren't talking about whether it rained yesterday. We are talking about a fundamental shift in the 30-year average.
Now, let's unpack temperature. It's not just hot or cold.
It's the degree of hotness or coldness. But the engine driving it is insolation.
Insolation, that's I-N-S-O-L-A-T-I-O-N. Not insulation like the pink stuff in your attic.
Right. It stands for incoming solar radiation. This is the energy coming from the sun that the Earth intercepts. And the distribution of this insolation is the key to all global geography. It decreases from the equator towards the poles.
Because the Earth is curved?
Yeah.
The sun hits the equator directly, like a direct punch, which sort of glances off the poles at an angle.
Exactly. Think of a flashlight. If you shine it straight at a wall, the light is a small, bright circle. That's intense energy. If you tilt the flashlight, the light spreads out into a long, faint oval. It's the same amount of light, but spread over a larger area, so it's less intense. That's what happens at the poles.
That explains why the poles are covered in snow. If they got the same insulation as the equator, they'd be tropical.
Yeah.
And this gradient, this difference in heat, drives everything.
Everything. It drives pressure, it drives wind, it drives ocean currents. Nature is always trying to move heat from where there is too much at the equator to where there is too little at the poles. The text also mentions something interesting about cities versus villages. The urban heat island effect. Although they don't use that exact term, they describe it perfectly.
Yes. They mention that concrete and metals in buildings and asphalt on roads absorb heat during the day and release it at night.
It's about thermal mass. Concrete holds heat much better than soil or grass does. Also, all those high-rise buildings trap warm air. They block the wind that would normally cool things down. So cities become these literal islands of heat.
This is why if you look at a temperature map of a region, the city is just a glowing red dot compared to the green surrounding.
Exactly. Let's connect this to the PYQs.
Let's.
There is a fantastic connection to the 2013 General Studies Paper 1 for mains. Question 2 asked about temperature inversion. Normally, temperature decreases as you go up. We just learned that in the troposphere section. But sometimes that reverses. Warm air traps cold air below it.
Like putting a lid on a pot.
Yes. This often happens in valleys or during long, clear winter nights. Now, while the Class 7 text doesn't go deep into inversion, understanding the basic behavior of temperature, that the ground heats the air from below, is the prerequisite to understanding its inversion. If the ground cools down rapidly at night, which happens in winter, the air touching the ground gets cold and dense while the air above stays warm. Boom inversion. This traps pollutants and causes smog, which is a massive issue in places like Delhi.
And the 2025 Prelims Paper 1, question 27, talks about isotherms, lines of constant temperature bending.
Yes, it discusses how isotherms bend equatorward or poleward when crossing land versus ocean. This goes back to the concept that land heats and cools faster than water. The NCERT sets the foundation. Temperature of the atmosphere changes not only between day and night, but also from season to season. Land reacts fast, oceans react slow. That differential heating is what bends those lines on the map.
Also, the 2025 GS1 paper, question 6, asks about the ecological and economic benefits of solar energy in India.
Which is directly linked to insolation. India is a tropical country. We have very high insolation. We are geographically blessed with solar energy. Understanding that we have this resource because of our latitude is the geographic basis for that policy question. You can't write a good answer about solar policy without understanding the geography of insolation.
Okay, let's move to the invisible force, segment 4, air pressure and the wind machine.
Air pressure is one of those things we take for granted. The text says air presses on us with great force from all directions.
But we don't collapse like an empty soda can. Why?
Because our bodies exert a counterpressure. We are pressurized from the inside. Our blood pressure, the air in our ears and lungs, it pushes back. The NCERT gives a gruesome but memorable example. Astronauts on the moon.
Oh yeah, this part is wild.
The moon has no atmosphere, so there's no air pressure. If an astronaut took off their suit, their blood vessels would burst. Not because of the cold or heat, but because the counterpressure of their body would push out against a vacuum. The body pushes out, nothing pushes back, and, well...
It's a graphic way to remember it. So, pressure exists. How is it distributed?
Vertically, pressure falls rapidly as you go up. That's why your ears pop at a plane or on a mountain. The air is thinner, less weight pressing down on you.
And horizontally. This is where the weather gets made.
This is the most important concept in meteorology. High temperature creates low pressure.
Wait, break that down for me again. Hot equals low pressure. That seems backwards.
It does, but think about a hot air balloon. When you heat air, the molecules get excited and move apart. The air expands and becomes lighter, less dense. Because it is lighter, it rises. When air rises, it leaves less air pressing down on the surface. That void is low pressure.
And rising air cools, condenses, and forms clouds. So low pressure usually means cloudy, wet weather.
Correct. Conversely, low temperature creates high pressure. Cold air is dense and heavy, it sinks. Sinking air suppresses cloud formation. It literally squashes the clouds before they can form. So high pressure means clear, sunny skies.
Okay, so hot air rises, creating low pressure and rain. Cold air sinks, creating high pressure and sun.
Generally, yes. And here is the golden rule of wind. Air always moves from high pressure to low pressure.
It's nature trying to balance the scales. The high pressure area has too much air, the low pressure has too little, so the air rushes in to fill the gap.
Exactly. That movement is wind. If the pressure difference is small, you get a gentle breeze. If the pressure difference is massive, you get a hurricane. The text divides winds into 3 types. First, permanent winds.
These are the reliable ones, right? The trade winds, westerlies, easterlies. They blow constantly year-round in a specific direction.
Then you have seasonal winds. These change direction with the seasons. The classic example given is the monsoon in India.
Which is basically a gigantic land-sea breeze, isn't it?
It is on a continental scale. In summer, the land gets super hot, creating a huge low-pressure zone. The ocean is cooler, so it's a high-pressure zone. Wind blows from sea to land, bringing all that moisture and rain. In winter, the whole thing reverses.
And finally, local winds. These are small scale, like the land and sea breeze you get at the coast, or that hot, dry, dusty wind that hits northern India in the summer.
And let's link this to the exams. This is an absolute goldmine for PYQs.
Go for it.
The 2024 prelims, question 14, is about the Coriolis force. It asks if it increases with wind velocity and if it's absent at the equator.
Now, the answer chapter 4 talks about permanent winds like the trade winds, but it doesn't explicitly explain why they curve.
Exactly. This is the next step. The trade winds don't blow straight north-south, they deflect. Why? Because the Earth is spinning. That spin creates an apparent force called the Coriolis force. Imagine trying to draw a straight line on a spinning record. The line will curve. The UPSC asks you to layer that advanced concept on top of the NCERT basic concept, and the statement that Coriolis force is absent at the equator is correct. That's why cyclones rarely form right at the equator. They need that spin to get organized.
And the seasonal winds connect to the 2014 prelims, question 43.
The seasonal reversal of winds is the typical characteristic of. The answer is monsoon climate. That is a direct lift from the concept of seasonal winds in this very chapter.
I also see a connection to the 2013 GS1 question about hot deserts.
Yes, question 21. Major hot deserts in northern hemisphere are located between 20-30-degree N latitudes and on the western side of the continents. Why?
Okay, so why is that?
It connects to the global pressure belts. That 20-30-degree latitude is a subtropical high-pressure belt. Remember, high pressure means sinking air. Sinking air means no clouds, no rain, so you get arid conditions.
It's a permanent no-rain zone.
Pretty much. And the NCERT map of major pressure belts in figure 4.4 actually shows this high-pressure zone. If you study that map, you understand the location of the Sahara, the Thar, the Arabian Desert. They are all sitting under that big high-pressure belt.
It's amazing how a 7th grade map holds the key to a mains question.
That is the beauty of these deep dives. The basics are the keys to the kingdom.
All right, let's get wet. Segment 5. Moisture, rain, and disasters.
Moisture is all about humidity. Humidity is just water vapor in the air. The key physics point here, and it's a big one. Warmer air can hold more water vapor than cold air.
That explains why a hot, humid day feels so gross and sticky. The air is full of water.
Right. Think of the air as a sponge. Warm air is a big, giant sponge. It can soak up a lot of water.
Yeah.
Cold air is a tiny little sponge. So when warm, moist air rises, it starts to cool. It shrinks from a big sponge to a small sponge.
Right.
Suddenly, it can't hold all that water anymore, so it has to squeeze it out.
And that squeezing out is condensation. Clouds form.
And when the droplets get too heavy to float, they fall as precipitation rain, snow, sleet, hail. The text outlines 3 types of rainfall based on how the air gets lifted up to cool down. Figure 4.5 is the visual here.
First, convectional rainfall.
This is the simple one. Sun heats the ground, air gets hot, air rises, cools, rains. This happens almost every afternoon in the equatorial regions. It's like a boiling pot of water.
Second, relief or orographic rainfall. Oro means mountain.
Moist air from the sea hits a mountain barrier. It can't go through it, so it has to go up and over it. As it climbs the mountain, it cools and rains heavily. This happens on the windward side. This is why Mumbai, on the windward side of the Western Ghats, gets soaked in the monsoon.
And the other side of the mountain.
The air crosses the peak and starts to go down. As it goes down, it warms up. Warm air is a big sponge again, so it stops raining and actually becomes very dry. This creates a rain shadow on the leeward side. That's why Pune, just a few hours from Mumbai, is much, much drier.
And third, cyclonic rainfall.
This happens when a warm air mass meets a cold air mass. They don't mix easily because of their different densities. The lighter warm air is forced up and over the heavier cold air. This lifting creates fronts and leads to the widespread, often drizzly rain we see in cyclonic storms.
Speaking of cyclones, the NCERT includes a brutal case study, the Odisha supercyclone of 1999. It's a very sobering read.
It is a crucial read for UPSC because it shifts from theory to disaster management. This cyclone originated as a depression in the Gulf of Thailand. It hit the Odisha coast with wind velocities of 260 kilometers per hour.
260 kilometers per hour. That is unimaginable. That's not wind. That's like a solid wall of air hitting you.
And it lasted for 36 hours. But here's the critical point. It wasn't just the wind. The text highlights the tidal surge, a wall of water 7 to 10 meters high that traveled 20 kilometers inland.
That's a 3-story building made of ocean moving 20 kilometers inland.
Exactly. It destroyed paddy crops, but the long-term damage was salinization. The salt water soaked into the soil and made the farmland infertile for years. It poisoned the land.
It also mentions the destruction of mangrove forests between Paradeep and Konark.
Which is a tragic loss because mangroves are nature's defense against such surges. They are the speed bumps for cyclones. They absorb the energy. Losing them makes the next cyclone even deadlier.
Let's link this to the PYQs.
The 2013 prelims, question 72, asks about thunderstorms. It asks if they are produced by the meeting of cumulonimbus clouds or violent upward movement of air and water. The answer lies in the violent upward movement. That's a convectional dynamic we just discussed.
And the 2019 prelims, question 40, talks about wetlands and the Ramsar Convention.
This connects directly to the flood control aspect. Wetlands, like the mangroves destroyed in Odisha, act as sponges. They absorb floodwaters. The UPSC focuses heavily on the function of these ecosystems. The destruction mentioned in the 1999 case study is exactly why we have the Ramsar Convention today, to protect those natural buffers. The exam asks about Ramsar sites because they are the solution to the problem described right here in NCERT Chapter 4.
And finally, 2025 prelims again, question 28 regarding clay and chalk and water absorption. While it's geomorphology, it relates to how water interacts with the lithosphere after the rainfall happens.
Everything is connected. The rain falls from the atmosphere, hits the rock of the lithosphere, runs off into the hydrosphere, and affects the plants of the biosphere. It's one system.
So we've gone from the gases we can't see, to the layers above us, to the pressure that crushes us, to the winds that cool us, and the rain that feeds us, or sometimes floods us.
It's a complete system. You pull one thread-like increasing CO2 just a little bit, and the whole tapestry changes.
So what's the so what here for our UPSC listeners? Why should they care about the troposphere when they're studying international relations or polity?
The so what is that you cannot ignore the basics. You might be reading high-level current affairs about the polar vortex freezing America or El Nino causing droughts in India. But if you don't understand the basic high-pressure, low-pressure mechanics from NCERT Class 7, you are just memorizing jargon.
You don't actually get it.
You don't get it. You're not learning. This chapter provides the logic. The Coriolis force, the greenhouse effect, the monsoon mechanism, it all starts here.
Well said. It's the foundation of the house. You can't build a roof without it.
Exactly. And for the mains exam, your ability to explain complex phenomena simply using these basic concepts is what gets you marks. The examiner doesn't want jargon. They want clarity. NCERT teaches clarity.
Okay, that wraps up our deep dive into air, a massive topic distilled into an hour. Before you go, a quick reminder to please subscribe to Simplified UPSC by PPP. It helps us reach more learners like you.
And if you can, please do support us on Patreon. We want to keep the lights on and the content flowing. The link is in the description.
Check the public telegram for those free notes, and DM us to join the private library for the premium experience.
And I have a question for the listeners to answer in the comments. We talked about the 5 layers of the atmosphere. Which one fascinates you the most? Is it the action-packed troposphere where we live, or is it the silent, thin exosphere where space begins? Let us know.
Here's a final provocative thought to leave you with. We learned that CO2 is essential for warmth, but dangerous in excess. We learned rain brings life, but cyclones bring destruction. The atmosphere is a story of these delicate balances. As you study geography, ask yourself, how does human activity tip these delicate scales?
And more importantly, do we have the power or the wisdom to engineer a way back to balance, or are we just passengers on a ride we can't control?
That's the ultimate question. Can we be the stewards of the system?
Or just its victims?
Thanks for listening. We'll catch you in the next deep dive.
Stay curious.
And keep breathing.